Well, the first thing to be said is that people who are interested in rocks are a hardy group. I said to Carol this afternoon, if 10 people show up tonight, I'll be so happy. But thank you all for coming out in this kind of weather. It's a struggle, and I hope you're cool enough. There's plenty of water, and if you feel that you'd like to have something more to drink, even during the lecture, I'm sure Bill wouldn't object if you feel you'd like to have another cold drink. So by all means do that. So without any further ado, Bill is going to be talking this evening about, among other things, the anticlinal fold here in High Falls, which we all know and love. And we're so fortunate that one of our poets, Matt Sparling, is here and is going to read a poem that he wrote about that very rock formation. So Matt, where are you? Okay.
Try to do this without the mic and away from that steering wheel. Can everybody hear me?
Yes.
Everybody hear me? Can you hear me there in the back?
Yes.
Okay, I'll speak softly. I want to thank Richard and Carol for inviting me to do this. I have to confess, though, when they first invited me to do this, I thought they were inviting me to be the opening act for a rock hunt. Seriously, if you think I wrote this poem for this event, the strange thing is I wrote this poem in April and I had no idea this event was going to happen. And then I bumped into Richard and Carol putting up the sign at the corner about this event, and they asked me if I had any poems I could read, and I said, well, it just so happens. So here I am. This is called Anticline. First heard of earth science over 60 years ago in school. And didn't I admire the upfolded layers of rock below the falls I could see from the road? Such a clear example and large. So if I could stand near, I'd have been dwarfed, as I would be dwarfed now. That arch of rock still visible from the road as I drive by and remember anticline and syncline, stalactite and stalagmite, all the wonders of the world. Thank you.
Well,
we're going to get to that. That's later in the talk. And we are going to consider all of the wonders of the world, which we can find right here. And that's one of the great things about geology, is that rocks are everywhere. And they always remember what happened. You just got to ask them, and you got to listen to what they say. And hopefully we'll dive a little bit today into how you can listen to what they have to say. So we're here for the High Falls Conservancy. This is the third installment in the series. Every Thursday this month we're talking about some aspect of High Falls geology. And tonight we're going to talk about a tectonic train wreck to try to understand why is the landscape here so crumpled up. And we will, the stars of the show tonight are the rocks that we talked about last time, but we only introduced them really in a very intellectual way and kind of a conceptual way, and that I realize is not enough. So I hope that everybody took some rocks out of the bucket on your way in. I really hope that everybody has got 4 rocks in their hands, because we have 4 really distinctive and important layers of rock in the local neighborhood, and we have 1 chunk of each one of them in the back. And so I really hope you will get up close and personal with the rocks today. So everybody go get your rocks. Yes, everybody needs to have 4 rocks in their hand.
Get out of the way here.
And the buckets are not labeled, but you'll notice that they all look different. Just like you'll recognize all your children, you can tell them apart. Hopefully you'll be able to tell each one of these 4 rocks apart by the end of our discussion. I mean, my kids, I still forget their names, but I know which one of them is which.
I'm just going to jump in here real quickly. While many of you are back by the sign-in desk, if you have not signed in and indicated whether you'll be attending the reception for Bill and his wife Judith next Thursday, immediately after the lecture, please do so. You don't have to do it right now, but if you're back there and haven't done it, do it please. And then for the others, if you haven't, on your way out, you can do that. Okay, thanks.
And so as you're back there at the bucket, the buckets are organized from left to right, like you read a book. You start on the left with what happens first, and you wind up at the end with what happened last on the right. And you should have a white rock, a red rock, a blue rock, and a yellow rock, or green, depending on how you... Okay, looks like we're getting everybody back towards their seats. That's good. All right, so if we started at the left of the bucket, like reading a book from left to right, we're going to read the column of rocks like Japanese script. We're going to start at the bottom because that's the oldest stuff. That's what came first. And Mary, if you put the next one, please. Oh, before we do that, I'm going to talk a little bit about particle size because it's really important for a sedimentologist. A lot of what the rock can tell you is contained in the size of the particles because it takes more energy to move a bigger particle. So the size of the stuff in your rock tells you about how much energy was in the mostly water that's moving it around. But I just give you a little bit of geological education here. I am by training a sedimentologist. That's my background, and we are really simple-minded, brute force kind of people. And we only understand things in very simple terms. Like for size, is something twice as big as the other one or half as big as the other one? I can handle that. Twice as big, half as big. So you see a series of circles there. They happen to be, according to PowerPoint, 2, 1, half, and a quarter centimeters. But the point is just their relative size to each other. And going from one category to the next, you're moving by a factor of 2. You're either getting twice as big to the left, or you're getting half as big to the right. So next slide. And if you want to, but we still like to claim that we're scientists and we have to look fancy. So, we use powers of 2. The exponents that we just put up there, that's another way of writing 2, 1, half, and a quarter is 2 to the first power, 2 to the 0 power, 2 to the minus 1, and 2 to the 2. Now, to be even a little more complicated, we then change that middle row, next slide please, to just the exponent, and we change the sign of it. So now this, if any of you are shooting enthusiasts, and I think the guys in Iowa who made this system back in the 1920s probably were hunters. This is like shotgun pellets. The bigger number, the smaller number is the bigger pellet. And here so as you get to, like number 2 shot, that's big, hefty shot for geese. And number 6, that's little for quail. And 9, that's like powder, just to scare people away. Same thing with the size of the particles. So when you see the numbers on the next chart, that's how they go. Minus numbers mean really big particles, and then as you get to positive numbers, the larger the number, the smaller the size. So A guy named Charles Wentworth at the University of Iowa set this system up in 1922, and it kind of makes sense. If we go to the next one, you'll see some pictures that describe the particles. And this is just to give you some physical intuition for what I'm talking about when we get there. That if I say coarse sand, that has some intuitive meaning, but it also has a very specific numerical inference for a sedimentologist. And it's coarse sand is twice as big as medium sand, and medium sand is twice as big as fine sand, and so forth. All right, so let's go on to the next one. There's just a prettier picture in color to help calibrate your eye. Okay, now we'll go on to the next slide. We'll get back to the actors in our drama today, starting at the bottom with the Schwungen conglomerate. That's the white rock you have. That is a gravel stone, or it is a rudite, if you really want to get into the lingo, because it's coarse, it's rude, it's crude, it's rude. It's a rudite, and that's really the term. The next rock in the order of events is the High Falls Shale. That's the red one, and it is a mudstone. So its particles are the size of silt and clay, which together have the name mud, which is actually a very precise sedimentological term. And then sandstone, the next rock up the pile, that's the blue one. It's the Binnewater sandstone. And the individual particles in that rock are somewhere between a 1/16 of a millimeter and 2 millimeters. That's the precise meaning of sand. And we'll see in a minute that we're on the finer end of the spectrum in the sandstone. And then the next rock above that is the Rosendale Formation, which is a dolostone. It's a kind of carbonate we discussed last time. But let's see, back up. All right, there we go. Let's start with the Schwungen conglomerate. There you go. So your white rock should look like that, and your individual piece will vary. But the salient points are that it will have pebbles and cobbles as clasts, and clast just means that's like the chocolate chips in the chocolate chip cookie. And the matrix, the rest of the cookie, is coarse to medium sand. So that means it's from about 1 millimeter down to about 1/4 of a millimeter in size. And as you will see, that's a pretty tight rock. It's a pretty tough stone because it is all cemented together. And when we get to the Binnewater sandstone, we'll talk about cement in a little more detail. Okay, going up the pile, the next one is the High Falls Shale. And that's a mudstone, meaning it has silt to clay sized particles. And siltstone is the reason that we draw the line between very fine sand and silt is because that's actually where you can't see with a magnifying glass anymore. Even with a 10 power loop that most geologists carry around, that's the size at which you don't see the individual particles anymore. That's where silt starts. And you'll notice that your rock is very flaky. It's like, you said it was like phyllo dough. And in fact, when I collected this, I didn't even have to use the big hammer on the table. I just picked it up. I just flaked it off with my fingers from the outcrop. Now, to make sure we didn't have any confusion, I only collected red High Falls Shale. So you all got, but if you go down to the falls, you'll see that there's some yellow and there's some green too. So it comes in different colors, but for tonight's purposes, we just got red. Now, if you were to pick up that bucket, out of the 4 buckets, if you picked up the red shale one, you would see that it is by far the lightest bucket of all of them. This is the lowest density stuff, and we'll try to explain why that should be the case. So if we go to the next, let's investigate that phenomenon of the lowest density. Next one, please. So this is a photomicrograph, not of this shale, but a pretty similar one. And we have 2 pictures on the left that have a scale bar of 1 millimeter. So you see that these are indeed kind of silt and clay-sized particles. And then the photos on the right are enlarged by 5 times. And the enlarged picture shows you that all the little white spots here are little critters. They're little tiny fossils. whose shells are made out of calcium carbonate. And I suspect that the reason this shale density is so low is because I collected it from an outcrop that's been sitting around in the weather. You know, it's got rain and everything pouring on it, and these little fossils, I think, have all dissolved away. And so where they used to be, there's nothing anymore, and that's why the rock is very light. I mean, not very dense. All right, next one. Now the Bitterwater sandstone, on the other hand, is very dense. You pick that bucket up and you got to do a little bit of work. The individual particles that make it up are fine sand sized. You can just barely see them with your naked eye. Paper I read about it says that they're on average about 1/10 of a millimeter. And the rock itself is very tough and hard to break. I had to do some, I borrowed Richard's big hammer. I didn't find mine, but I was really sweating by the time I got done because it's hard to break. And if you see this little ridge on the sample that I took the picture of, and I imagine that your piece will have a kind of a sharp edge like that too. That's called a conchoidal fracture, and that's usually indicates a material which is very strong in every direction. It doesn't have a preferred area of weakness. And the reason, and so you see that it has this sort of broken glass shape of the hand sample, and if you take it outside in the sun, you'll see that it's really sparkly. That's one of its salient characteristics, is that it's really sparkly. And it's the highest density of the four formations. If you pick up that bucket, it's really heavy. So let's see if we can explain why that's the case. Why is it very tough and hard to break? Why is it sparkly? Those two things together explain why it has the highest density. So next one, please. Imagine that you can magnify the sandstone in your mind's eye up to so that the individual sand grains are the size of golf balls. And what I want you to focus on in this picture is the shape of the holes between the golf balls, the pore space of the rock. So you get a feeling for kind of the geometry of the pore space. Now, next slide. Imagine a geode that geode is sitting on somebody's hand. So it's got a big size. It's even bigger than the holes between the golf balls. But the shape of that hole is just like the shape of the pore space between the golf balls, which is just like the space between the individual very fine sand grains in this rock. And just like this geode is coated with quartz that is showing perfect pyramidal quartzy terminations, the same thing is happening in the pore space of your rock. And that's the sparkly bit. That's why it is so sparkly. So the reason this rock is so tough, the reason it's so dense, is because all the pore space in between the individual particles has been filled up with quartz cement that has little pyramidal terminations that sparkle. All right. So now you know. And now the last one, the Rondout Dolostone, it's the highest part of the pile that we've been considering in these lectures. It's the very famous rock of the neighborhood that was used to make Rosendale cement. And it is a carbonate. As we discussed last time, it's precipitated out of seawater in shallow, tropical, warm oceans. And then it is, because it can be chemically precipitated, it's easy also to dissolve it. And many of I tried to get samples that mostly have little holes in it. So if you look at your sample, you may find that it has some little holes in it, and that represents places that have been dissolved away. And you may also notice that your piece has some pretty, either a sharp line within it or a flat edge where it broke on a layer. And this shows you something about the periodicity or the episodes of deposition that were responsible for that rock as it was depositing in that shallow, warm sea. So the point of all this discussion was just to give you a little more personal appreciation for those rocks and not just have it be some kind of abstract concept on the screen. Now we're going to go to abstract concepts. We'll try to make it as real as possible, but the stuff we're talking about today is at a big scale. So, yes, sir. So the very top layer where the fall goes over the top, that is the Beecroft limestone. I actually did collect some of that, but that hasn't been part of the lecture, so I didn't bring those today. But that's also a really tough rock. All right, so we'll go back just a quick, yes, sir.
Can you equate the density to the difficulty of drilling the soil?
Yes, absolutely. All right, so for those of you who've been here on the previous episodes, I won't belabor this point, but I just bring it up if anybody hasn't come before. If we think about the inside of the Earth, you can have a mental model like a hard-boiled egg. Next one. There is a crust on the outside, which is a very, very thin shell of the Earth. That's what we stand on. It's very low density, floating on the next layer down, which is the mantle, which is kind of like the white of the egg. At geologic timescales, it is a fluid that can flow. And then in the middle is the core, which is really high density, very heavy. That's why it's in the middle, because it's so heavy. And it is hot. And everything that we're going to talk about today happens because the center of the Earth is hot and the outside is cold. As a result, so what happens when you have something that's hot on the bottom and cold on the top? You get convection. So you get hot stuff near the bottom where it's hot. It expands, it gets less dense, and therefore it rises to be replaced by the cold stuff from the top, which is contracted, it got more dense, and it falls to the bottom. And then you have a cycle that is set up. We know it from our own personal experience as a rolling boil in a saucepan. But that's happening in the Earth too. On a lot longer time scale, but it's the same physics. The mantle picks up heat near the outer core, it expands, it gets less dense, it rises. Some of it makes new oceanic crust at a mid-ocean ridge, and and then there's a traction. This convection cell in the mantle is dragging the crust along with it, and so it drags the tectonic plates around. New oceanic crust is made at mid-ocean ridges, and it is destroyed at trenches. So what we're going to talk about today is how did this process of dragging the Earth's crust around on top of this flowing mantle create the landscape that we see today in the High Falls area. So, next slide. This is a summary by a professor named Steve Marshak, who did his PhD in this area about 40 years ago, of all the things that happened right here on our edge of North America since about 1 billion years ago. And we'll step through, and the diagrams give you the same kind of tectonic setting that we've seen in previous diagrams, and I'll show you an example on today's Earth where the same thing is happening. So, 1 billion years ago, there was a supercontinent. This is before Pangaea. This was called Rodinia. All the different fragments of continents had all the bumper cars had slammed together in the middle of the bumper car ring, and they were stuck together, and it was called Rodinia. And then it started to break apart. Oh, sorry, next one. 600 million years ago, it started to break apart. And if you go to the next slide, and that splitting apart is exactly like what is happening in Africa today. So along the East African Rift, you can see these lakes that are accumulating as this part, Kenya, Somalia, etc., East Africa is pulling away from the rest of the continent, and it's breaking up. And that's what happened about 600 million years ago right here in our neighborhood. So then it opened up, just like the Red Sea. The Red Sea is an example where you get to real, honest-to-goodness oceanic crust formation, and then ultimately you get a big ocean. That all happened, but then some of that oceanic crust that was created by the opening of the Paleo-Atlantic then started to be consumed beneath an island arc. If we go to the next slide, that's happening today near Australia. So here's Australia in the way we're used to looking at it, and here's the little island arc that's approaching, like this island arc. But if you go to the next slide, I'm going to flip Australia on its side so that it looks like, it has the same kind of orientation that our neighborhood would have had back then. So next slide, please. So the cross-section here at 420 million years is like what's going on in Australia today. You have this bit of continental crust, you have a trench that's going down underneath an island arc, and eventually that island arc is going to wind up stuck onto the edge of Australia, like what's happening down here, and that's going to be this cross-section. The tectonic mountains are the result of this island arc sliding up on the edge of North America. So that's one collision that made one kind of deformation. Now back behind that island arc, on this cross-section, it's way out here, but after this thing has been plastered onto the edge of the continent, now we have another piece of exotic crust out here, and it is ultimately going to also accrete because this oceanic crust and that oceanic crust are going to break off and start subducting. So we have a double-edged subduction zone. And if you go to the next slide, that's like what's happening right here in the Sunda Sea to the northwest of Australia towards Indonesia today. So you have a trench and a trench with the oceanic crust in between just falling away into the mantle. And when that oceanic crust was completely consumed, now that little bit of exotic crust, which had become a volcano and a volcanic arc in the process, that got slapped onto the edge of North America, and that's called the Acadian orogeny. So we had two distinct collisions of other stuff with the edge of North America that started deforming the rocks, the four rocks that you have in your hand. And then the big daddy train wreck happened. We had Africa coming in behind, and that crunched the whole thing up at 270 million years ago to assemble the continent of Pangaea. So if we go to the next one, the best example of a continent collision like this one at 270 is India smacking into Asia. And we all know what the Himalaya mountains look like. That's Mount Everest, 20,000 meter mountains. That's a big old mountain range, and that's what we had here just to our east at 270 million years ago, which is just after the last rocks that you have in your hand. All right, so now we go to the next slide. You might remember this from last time. The best example that I can find that describes what was going on here is the collision of Arabia with Asia. If we go to the next slide, we're going to zoom progressively in, and the area around here that we'll examine is kind of along this cross section. All right, so next slide. And now once again, I've spun it around so that it has kind of an analogous orientation. And we're looking at the collision of one continent with another. Now we'll zoom in one more step, and you can start to see that there's this rumpled up edge on one of the colliding plates. And we'll zoom in one more step. There we are. And now let's compare this topographic grain on today's Earth in the Zagros Mountains of Iran with a map of right here. This is a map from 1952 by a guy named Newton Shute. High Falls is here, Kingston is up here, and you see all this stripy stuff in between. So I hope that there's at least a visual, you get the visual comparison that the stripy stuff on this map has the same kind of texture as this landscape, which is in the Zagros Mountains, which is clearly the result of a continent-continent collision. Now, if you'd like to have a better mental model of what's going on, oh, and of course, there is the anticline. So we're, this is right here in our own backyard. This is an example of this kind of thing. But what does that even mean? What is an anticline? Somebody asked that. We're headed there. Okay, next slide. So if you need a mental model for what does this map pattern on the geologic map mean, it's like this. I didn't realize that there's this whole Game of Thrones fandom, and there's like virtual worlds where you can play Game of Thrones. And I found this crumpled up carpet imagery from, you can use this to I don't know, furnish your castle in the Game of Thrones game. But anyway, I think anybody who's walked in and slipped on the carpet can appreciate this rumpled up carpet. And that is exactly what this geologic map is representing. Those different colored stripes on the map represent folded up layers of rock, just like this folded up or rumpled up carpet. So let's go to the next one. Let's look at what would happen if we took a bulldozer and just bulldozed away a big trench across our neighborhood right at Williams Lake, and we got down in the trench and looked at it from the side. What would it look like? Well, like that. This is from a guy named Kurt Burmeister who did his PhD on this very neighborhood. And this is essentially what you would see if you dug this trench and looked at the rock layers from the side. And they're all rumpled up. So let's see what that looks like on the real landscape. Next one, please. Oh, and here's where we get to the vocabulary part. So what is an anticline? An anticline is one of these folded up piles of rock. One of these squished up piles of rock. And we can describe a thing called the axis, which is where the layers are bent the strongest. And then we can look to see whether the limbs, that's what you call the bit on either side of the axis, if they're dipping away from the axis, then it is an anticline. The limbs are inclined away from the axis, so it's an anticline. And then the corresponding structure, the next one, is a syncline. Again, there's an axis which represents the locus of the most intense bending, and then you look to see the limbs are inclined toward that axis, and that is a syncline. And clearly, you can have a limb which belongs both to a syncline and to an anticline. And we'll see some examples here on our local landscape in the next slide. So we're going to zoom in. I've got High Falls, this is Google Earth. I've got High Falls highlighted down here in the lower left-hand corner. And if you go back to Rosendale, turn left on Highway 7, Binnewater, or County Road 7, Binnewater Road, heading towards the Women's Studio Workshop, you'll come up to Williams Lake and Fourth Lake. Next slide, please. That's the neighborhood that we're going to investigate next. Next slide. Let's zoom in. There's Williams Lake. There's Fourth Lake. And here's an inclined view, like flying over at about, 8,000 feet in an airplane, what Fourth Lake looks like. And I can't see it so well from this angle. I hope you can out there in the audience. But I hope you can see that there's a little topography. These little prongs that are sticking out into the lake, those are high, and obviously the lake is low, the water's in the low spot, and these little ridges are higher. So now let's draw a little bit on this map. You can see this promontory and this promontory, they line up with each other, and they line up with another promontory on either side of Williams Lake. That is an anticlinal axis. If we look at it from the side, that's the top of the fold, and the two limbs are dipping away from it. And that's why these segments of the lakes are there. Now, if you go to the next slide, and adjacent to the anticline is the syncline. And so you'll see that I've put some symbology on the axial trace. That's this thing. This is the surface expression of the axis. And I put these arrows pointing away to show that it's an anticline. And here I've got the arrows pointing towards each other to show that it's a syncline. But you'll notice that this arrow pointing into the syncline and that arrow pointing into that syncline could just as well be the arrows pointing away from the anticline. So they all go together. And if you look over here on Fourth Lake, you can see these trends. Here's one anticline, and then the lake itself, these lobes in the lake, those are synclines. So here's a question for y'all. What's going on there? What's that promontory? Anybody want to take a guess? So we've got this red line goes right through here. That's an anticline. The extension of the lake, that's a syncline. It is Binnenwater sandstone is the reason that is the rock that's there for sure. But structurally, what do you think is happening along that little ridge? Yes, it's another anticline. That's another anticlinal axis. And you'll notice if we look along this anticline that's coming along here, and there's a little gap where there's lake. So not only is there a fold that goes down to the right and down to the left, the axis of the anticline is dipping down a little bit and coming back up. And so this anticlinal axis is dipping down, and we just don't see it coming back up again. It just kind of goes down. Now we can take a look, next slide, on the rail trail just going along Fourth Lake, and we can see what the actual rock layers look like as they are part of these folds. Next slide, please. Now this is a picture from from before 1921. It was reproduced in a 1921 paper. This is a photograph made by a Princeton undergraduate student who was studying geology and came out for field camp to this area. And back then, at the turn of the previous century, 100 years before now, it was a whole lot easier to do geology here because the cement miners had cut down all the trees to burn cement to make Rosendale cement. So it was a lot easier to see the rocks. Unfortunately, we don't have a lot of modern photos because you just see a bunch of trees. But if you could take away those pesky trees and stand on the rail trail, you would see that the layers of rock are inclined, and this is just a little snapshot of the bigger folding that you can tell is going on in this neighborhood that is evident at this large scale. So next slide, please. So I didn't run too badly out of time. I want to give credit to the people who've done a lot of work in this area. Steve Marshak, who's now retired at the University of Illinois, did his PhD at Columbia on mostly from Catskill to Kingston. And then his student, Kurt Burmeister, got his PhD at Illinois. Now he's a professor at Sacramento State. He did the area from Kingston down towards here. And then Alex Bartholomew, who's currently a professor here at SUNY New Paltz and is he's probably the world authority now on the actual ages of the different rocks. So I got a lot of help from all of these guys, so we want to make sure to acknowledge that contribution. So we now have enough time left for questions. I think that's a good thing. I will put in a plug for next week's episode, where we'll talk about everything that happened. So what we just discussed, that's kind of the biggest deal that's happened around here in the last 600 million years. But a few things happened after that. There was the supercontinent broke up, there was mass extinction around the whole world, there were glaciers, the Catskills came up, a few minor things since then, and we'll talk about those next time.
Bye.